Okay, hello everyone. Welcome to the live problem solving session for week 4 of the course Computational Commutative Algebra. So, my name is Siddhartha Pramanik. I am a PhD student from the Department of Mathematics, IIT Kharagpur. Okay, so let's start by listing the topics which have been taught in this week 4. We started with some basics about the module theory, like what are exact sequences and all those things. Then we have seen about the Noetherian modules and some properties of this type of modules and some equivalent conditions for a module to be Noetherian. And after that, we moved on to the topic of localizations. So for that, we have defined multiplicative subsets of a ring. And using that, we have defined localizations of a ring, and after that, localization of a module. And we have seen some properties of this localization. And then we have seen one special type of ring known as local ring. And after that, we studied about the famous determinantal trick. And the celebrated Nakayama's lemma, which is very useful. So we denoted it by NAK, Nakayama, Azumaya, and Krull. And we have seen one consequences of this Nakayama's lemma. Then we studied about some geometrical facts uh, about the prime spectrum of a ring. So we have defined one topology known as Zariski topology on the prime spectrum. So Zariski topology on spec of R and some properties of this topology. And then one uh, particular type of topology, some irreducible topological spaces and so on. So irreducible topological spaces. So these are the topics which has been done in the week 4. Now let's start by solving some problems based on these topics. So the first problem is about Noetherian modules. So let M be a Noetherian module over a ring uh, R, and phi from M to itself be a R linear map, means it is an R module homomorphism. Then so that if phi is surjective, then phi will be automatically injective. So that means phi will be an isomorphism. So phi is an isomorphism, means it is an R module isomorphism. So basically it says if you have a Noetherian module and if you have an module homomorphism from that module to itself, which is basically surjective, then that map has to be an isomorphism. So this is a useful property of Noetherian modules. So let's prove this. So it's very easy actually. So let phi is surjective. So phi is onto, and we have to show that phi is an isomorphism. So it is sufficient to show that phi is an injective. So we want to show phi is 1 1, and that means the kernel of phi is just the zero submodule of M. So we want to show that the kernel is 0. Now how to show that this kernel is a zero sum module? Using the Noetherianness of the module. So observe that phi is a map from M to itself. Okay. Now kernel is a submodule of M, and observe that uh, your kernel of phi, it is also a submodule of kernel of phi square. Means I mean phi square is also a map from M to M, and it is even not square, any power will be mapped from N to M, and this is an ascending chain of some modules. So kernel of phi q and so on. So this is an ascending chain of submodules of M, but the module M is Noetherian, so this chain uh, has to stable at some point. So since M is Noetherian, there must exist some n, a natural number, such that okay, let's take it as k. So such that kernel of phi power n plus 1 will be equals to kernel of phi power n for all n greater equals to k. So that means after certain stage all these sum modules will be same, all the sum modules will be equal, and I'm choosing that stage to be k. So and also observe that also since okay, now okay, let's focus on the kernel. So we want to show that this kernel is 0. So let's take an arbitrary element and prove that that element is 0. So now let x belongs to kernel of phi. Now this is a submodule of M. Now that will imply uh, there exists some y belongs to M such that phi power n naught y is equal to x. So why this is? Because phi is onto, so that will imply phi power n is also onto, and this is for all n greater equals to 1. So pi power n is a surjective map from m to m itself. So pi power n is a map from m to m. I am taking an element x here, so it has a pre-image some y. So that is what I am doing. Now x belongs to kernel of phi, that means phi of x equals to 0. So this implies phi of, so 0 equals to phi of x equals to phi of n naught plus 1 of y. Okay, so let's not n naught, it is, let's take f as k. So k plus 1 equals to uh, sorry, so phi of k plus 1 y of y is equals to 0. So that will imply y belongs to kernel of phi power k plus 1. But from k onwards, all these kernels are same. So this is actually kernel of phi power k. So y belongs to kernel of phi power k. So x, which is same as phi of phi power k of y, that has to be 0. So our element x is 0, and x is an arbitrary element. So kernel has to be 0. So this implies kernel of phi is actually 0. So phi is 1 1, and hence phi is an isomorphism. So over a Noetherian module, if we have an surjective homomorphism, then that homomorphism has to be an isomorphism. Okay, so let's do the next problem. Question number 2. So again, let M be an R module where R is any ring. So here ring means commutative ring with identity. So let M be an R module, and let N1 and N2 subset of M be two submodules. B2 are submodules. So I have taken an R module and taken two submodules of that module. Now suppose M mod N1, this quotient, and M mod N2, the other quotient. So these are also R modules. So suppose that these are Noetherian R modules. Okay, then so that M mod N1 intersection into this quotient is also a Noetherian R module. So what is going on? So M is an R module, and N1 and N2 are two submodules such that the quotient M mod N1 and M mod N2 are Noetherian. And what we have to prove? That if we take this quotient m mod n1 intersection n2, this is also Noetherian. So that is our goal. So let's see this, how to prove this one. So from the lectures, uh, recall that if we take this quotient m mod n1 intersection n2, from this quotient we have a natural injective homomorphism to m mod n1 direct sum m mod n2. So this is an injective map. So this sequence is exact. So this is not a short exact sequence, but this is an exact sequence. Recall that this one uh, is an exact sequence of R modules. So this has been done in the lecture. So you just go back to the video and recall it. So that means this quotient can be thought as a sum module of this quotient. Also recall that since m mod n1 and m mod n2 are Noetherian, so these are Noetherian R modules, so their direct sum is also a Noetherian R module. So m mod n1 direct sum m mod n2 is also a Noetherian R module. So this is standard fact because so if you take any short exact sequence like 0 to L prime to L to L double prime, a short exact sequence, so then the middle one L is Noetherian if and only if both L prime and L double prime are Noetherian. So this is a very standard fact. So if you have not done, so just try to prove it. So we will use this one. So using that only we are claiming, since m mod n1 and m mod n2 are Noetherian, so their direct sum is also Noetherian. Because we can get this hot exact sequence like in place of L prime we can take m mod n1, and in place of L prime we can take m mod n2, and in the middle we can get the direct sum. So that will be short exact sequence. And also we have an exact sequence like this. So let's call it star. So from star, since this module is Noetherian, so every submodule of a Noetherian module is also Noetherian. So this has to be Noetherian. So now from star, it is clear that a mod n1 intersection n2 is a Noetherian R module. So we are just basically using this fact. So try to prove this on your own, or you may refer to any standard text. So this is also very easy. Okay, so let's move on. So now the problem number 3. So again, let R be a ring and M be an R module. So then, so that M is Noetherian R module, so that will imply the quotient ring R mod any letter of M in R is a Noetherian ring. Okay, so I should recall the definition of any letter of a module. So I will write it here. So any letter of M in R. So this is basically set of all those elements of the ring R such that R annihilates the whole module M. Means R kills M. So one can check that this is an ideal of the ring R, and M can be thought as module over this quotient ring also. So the problem is if we have a Noetherian module over a ring, then if we take the annihilator of that module and go modulo by that ideal, then we will get a Noetherian ring. So let's prove this. So how we will prove this? So first of all, since M is Noetherian, so M is finitely generated R module. So since M is Noetherian, so M is finitely generated. That means it has a finite generating set over R. So there exists some M1 up to MR belongs to M such that M is basically, so I will write this as R M1 plus R M2 plus dot dot R MR, or you can write this as just M1 up to MR. So this is basically the set uh, R1 M1 plus dot dot, okay, not R. So A1 M1 plus dot dot AR MR such that this A1 up to AR belongs to R. So basically we are writing this as generating set. So M1 up to MR is a generating set of M. So M can be written as this sum. Now let's use this fact. So that means every element of M can be written as R linear combination of this M1 up to MR. Then define let a map from, okay, just R. Let's take just R. Just R to M direct sum M dot 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 direct sum M up to R times. So we are taking direct sum of M up to R times. So how this map is defined? So this defined by, so phi of, okay, let's say A. Phi of A will map to AM1 comma AM2 comma dot dot A. So am1 am2 dot dot amr. So this is the map which we are defining. So this is a map from R to M direct sum itself R times. So now it's very easy to check that this is an R module homomorphism. So check that phi is a R linear map. So this part you just check it. It's just a routine check. So phi is a R linear map. Now what about the kernel of this linear map? So now what is kernel of this map phi? So definitely it is an ideal of R. So it is set of all those elements of R such that whose image is just 0, 0 tuple. So this is basically all those elements of R such that Rm1, okay, let's not take R. So again, let's take A. Set of all those elements A of R such that am1 dot dot up to amr, this tuple is basically the 0 tuple. So that means A belongs to R such that A m1 equals to A m2 dot dot A mr, all these elements are 0. So all those elements of R which kills every generator m1 up to mr of the module M. So A will basically annihilate every element of M. So A belongs to R such that A dot summation ai mi from I equals to 1 to R will be 0 for all a1 up to ar in R. So this is an arbitrary element of the module. This is the general form of an arbitrary element of the module M. So this means A belongs to R such that A M equals to 0 for all M belongs to M. So this means A belongs to R such that A M equals to 0. So this is all those elements of the ring which kills the module M. So this is basically the annihilator of the module in the ring. So this is basically annihilator of M in R. So we have got the kernel of this module homomorphism. Now let's use first isomorphism theorem. So by the first isomorphism theorem, so we have an injective homomorphism phi bar from R mod annihilator M to M direct sum R copies. Is so this is the induced map from phi. So that's why we are writing phi bar. So let's write the induced map. So the induced map is injective. injective R linear map. That means we can thought this quotient module as a submodule of this M direct sum itself R copies. So since M is Noetherian, so that will imply M direct sum over itself R times is also Noetherian R module. Now that will imply R mod annihilator M over R is also a Noetherian R module, because it is a submodule of a Noetherian module, so it has to be Noetherian. But what we wanted to prove? So we wanted to prove that this is a Noetherian ring. So it is a that means it is a Noetherian module over itself. But what we have proved? It is a Noetherian module over R. But we need over R mod annihilator M over R. But that is clear because all ideals are in on correspondence. So R mod annihilator M over R is a Noetherian ring, because we need to prove that every ideal of this is finitely generated, and every ideal of this is in one correspondence with the submodule of this as R module. So that is basically trivial. So R mod annihilator M is a Noetherian ring. Okay, now from this exercise, we can say something more about the ring R in some particular cases. So let's put that as remark. So I need one definition for that. So I will define it here. So first thing is faithful R module. So what do we mean by an faithful module? So an R module, let's say M, is said to be a faithful R module if, so let's take an R module M. We will call this module to be faithful if its annihilator over the ring R is basically the zero ideal. So that is the first definition. Then R module M is faithful if its annihilator is the zero ideal. Now the second remark. So if a ring R admits a Noetherian Noetherian module which is faithful, then R is a Noetherian ring. So how this is following? So suppose if you have a ring R and you have a Noetherian R module, and that module is faithful, that means its annihilator is 0. So from this exercise we can say that R mod annihilator M, which is 0, means R mod 0, which is R, that is itself a Noetherian ring. So a ring which admits a Noetherian faithful module, then that ring has to be Noetherian. So let's move on to next problem. So this was problem number 3. So problem number 4. So next topics are multiplicative subset and Nakayama and all those things. Okay, so let I be an ideal of a ring R, then the set S, which is defined as 1 plus I. So this is basically the set 1 plus A such that A belongs to I. So this set S is a multiplicative subset uh, of the ring R. So we can, first of all, this is a multiplicative subset that we have to prove. Second of all, since S is a multiplicative subset, so we can localize R at S. So also show that, so we can take the localization of the ideal, or we can take the image of I in the localization. Then this ideal is subset of the Jacobson radical of the localized ring S inverse R. Okay, so I will come to the second part, but let's prove the easier one, which is the first part. Okay, both are easy, so let's do one by one. So we want to show, so first part, that S equals to 1 plus I is a multiplicative subset. Multiplicative subset of R. So what we have to check? We have to check two things. So first one is that 1 belongs to S, and second one is if A and B is in S, then that should imply that their product is also in S. So let's check one by one. So both are trivial facts. So now 1 can be written as 1 plus 0, and 0 is in I. So this belongs to 1 plus I, which is S. So 1 belongs to S. Now let x equals to 1 plus A and y equals to 1 plus B belongs to 1 plus I, two elements. We need to prove that their product is also in S. So then what is x times y? This is 1 plus A times 1 plus B. So this is basically 1 plus A plus B plus AB. But I is an ideal. A, B, AB, all these elements are in I. So their sum has to be in I. So this belongs to 1 plus I. So this proves that S is a multiplicative subset of R. So this proves the first part. Okay, now the second part. So what is about the second part? So here you have the ring R. Here you have the localized ring S inverse R. Let's say the localization map as tau subscript S. So how this map is defined? R maps to R by 1. Now here you have an ideal I, and let's take image, let's take the extension of this ideal, which is generated by the image of this map, and we denote this ideal by just S inverse I. So we need to prove that this ideal S inverse I is subset of the Jacobson radical of the ring S inverse R. So we will recall what is Jacobson radical of S inverse I. So second part is, we want to show S inverse I is subset of the Jacobson radical of S inverse R. So what is Jacobson radical of the ring? It is basically the intersection of all maximal ideals of that ring. So okay, let me write that also. So Jacobson radical of S inverse R is basically intersection of all M, where M belongs to the maximal spectrum of S inverse R. So this is the definition, but we have an alternative description for the Jacobson radical. And what is that? So X belongs to Jacobson radical if and only if, okay, I will write it here. So recall X belongs to Jacobson radical of S inverse R if and only if 1 minus xy is unit uh, unit in S inverse R for all y belongs to S inverse R. So an element X of the ring S inverse R is in Jacobson radical if and only if 1 minus xy is unit for every y of the ring S inverse R. So we will use this equivalent condition to prove that this extended ideal is in the Jacobson radical. So one thing, that Jacobson radical is an ideal, right? And how this S inverse R I looks like. So now how this S inverse I looks like. So it is basically generated by A by 1 such that A belongs to I. And we will prove that all these generators is in the Jacobson radical. So if the generators is in the Jacobson radical, so the ideal generated by those generators is also in the Jacobson radical. So let A belongs to I and X by S belongs to S inverse R. So this is an arbitrary element. Okay, let's say Y. To let's say Y belongs to S inverse R. So then this Y has to be equal to S by S, where X belongs to R and S equals to 1 plus R for some R belongs to I, because S is in the multiplicative subset S, and every element of S has this form. So what we have to prove? then 1 minus a by 1 times y, which is 1 minus ax by s, which is same as 1 minus ax by 1 plus r, and this is same as 1 plus r minus ax by 1 plus r. So this is same as okay, now let's look at this element. So this is 1 plus a prime by 1 plus a. So this is some s prime by s. So what is localization? Okay, before that, so s prime comma s both are belongs to s. So that will imply tau s of s prime and tau s of small s are unit in the localized ring S inverse R. So S prime by S is a unit in S inverse R. So basically this element is unit. So this implies S inverse I is subset of Jacobson radical of S inverse R. So that is what we wanted to prove. Now this exercise is important because using this exercise one can prove the Nakayama's lemma without using the determinantal trick. So I don't want to do that, but this exercise you will find in the book of Atiyah and MacDonald. So if you are interested, you can do it. You just check the exercises of that book. But let's move on now. So next is problem number 5. So I will prove the Nakayama's lemma using a different method. So for that I need one result. So let's so it is from the problems in the practice problem set. So let's just use that one. So one result. So this is about simple R modules. So so let M be a non-zero finitely generated R module. So the result is then there exists a submodule n of M such that the quotient M mod n is a simple R module. Okay, so I need to define simple module. So I think it is defined in the lectures, but I cannot recall. So what is simple? Okay, I will define it here. So an R module M is said to be simple if it has no submodule except 0 and m. So except 0 and m, it has no other submodule. Then it is called a simple R module. And one thing, if m is simple, that will imply m is isomorphic to R mod some maximal ideal. So this is if and only. So m is simple if and only if m is isomorphic to R mod m for some maximal ideal of R. So this is the definition of simple R module. This is the description of simple R module or the structure, and this is one result, that if a module is finitely generated and it is non-zero, then there must exist a submodule of it such that this quotient is a simple R module. Now let's use this to give a different proof of Nakayama's lemma. So a different proof of Nakayama's lemma. So let's prove this. Okay, so let's recall this statement first. So the statement is, okay, so let M be a finitely generated R module and I be an ideal of R. So if I of M equals to M, then M has to be 0. So M is just a finitely generated R module, R is any ring, I is an ideal. If Im, this sum module, equals to M, then this module has to be 0. So that is the statement of Nakayama's lemma. Now let's see the proof. So proof is by contradiction. So suppose M is a non-zero R module. So if M is non-zero, so then M is a finitely generated non-zero R module. So by this result, there exists a sum module. So then there exists a submodule n of M such that this quotient is a simple R module. So such that M mod n is a simple R module. But a simple R module has a special form. So this module has to be isomorphic to some quotient by a maximal ideal. So there exists a maximal ideal of the ring R such that M mod n has to be isomorphic. Okay, so we need to be restrictive here. Sorry, we have to be restrictive. So here I subset of the Jacobson radical of R means it is contained in every maximal ideal of the ring R. So we are proving Nakayama's lemma in a particular case. So what, where we were? So M mod n is simple R module. So then M mod m has to be isomorphic with R mod the maximal ideal small m or script m. Now then R times R mod m, which is basically, sorry, I times R mod m, which is I mod m mod n, which is basically n plus im mod n, but im is equals to m. So this is n plus m mod n, because im is equals to m, and n is some module of m. So this is m mod n, and this is isomorphic with R mod m. So I times R mod m is isomorphic with R mod m. But what is I times R mod n? So this is basically m plus I mod m, and this is basically m mod m, which is 0. Okay, m mod m. But why m mod m? Because I is subset of m, and this is because I is subset of Jacobson radical of the ring R. So this is 0. So this implies R mod m is 0. So this is a contradiction, because it is a field. R mod m is a field, and a field cannot be 0. A field must have at least two elements. So let's see uh, one more application of this Nakayama's lemma. So it was, so we have not given any number to this problem. So earlier was 4, so it will be problem number 5. So this is also from the practice problem set. So let R comma M be a local ring, be a local domain, local integral domain, and K be its field of fraction. Then show that the maximal ideal times K mod R. So K mod R is an R module. So this is equals to K mod R. And one more question. If R is not a field, so that means uh, R is not equals to K, or R is a proper subset of K. Okay, R is not equals to K. Is K a finitely generated R module? So let's, it has two parts. Let's prove one by one. So we need to prove that M times K mod R equals to K mod R. So that is actually very easy. So what is m times k mod r? So this is basically r plus mk. Mk means extension of m to the ideal k. But k is a this is an ideal of k, but k is a field. So its extension has to be k itself. So this is r plus k mod r, and r is a submodule of k. So this is k mod r. So first part is very easy. Now the second part. Suppose r is not a field. So then r is not equals to k. So that means k mod r is not equals to 0. So if k is a finitely generated R module, that will imply its homomorphic image or quotient k mod R is also a finitely generated R module, because we can take the image of that finite generating set. But m times k mod R equals to k mod R. So by Nakayama's lemma, since k mod R is a finitely generated R module, so k mod R has to be 0. So which is a contradiction. So it contradicts the Nakayama's lemma. So k mod R cannot be, we have assumed that k mod R is not equal to 0. So this is contradiction. So that means k is not a finitely generated R module. Yeah. So one important thing I want to mention that, so in the Nakayama's lemma, the module has to be finitely generated. So if we drop the condition that this module is finitely generated, then the Nakayama's lemma may not be true. So there are examples. So you can try to find some examples in which M is not a finitely generated R module and Im equals to M, but M is non-zero. So actually this thing is giving you that counter example, because K mod R is non-zero, but M times K mod R is equals to K mod R. So there are other examples also. So one can try to find those things. So we have done Nakayama's lemma and all those things. Now let's see some basic and simple properties of local rings. So this is problem number 6. So let R comma M be a local ring. Then show that the only idempotent elements only idempotent elements in R are 0 and 1. Okay, I should recall the definition of idempotent elements. Okay, so I will write it here. So A belongs to R is idempotent if a square equals to a. So we need to prove that 0 and 1 are only such elements which are idempotent in a local ring. So let's prove this. So 0 and 1 are clearly idempotent elements. We need to prove that there are no other idempotent elements in a local ring. So let A belongs to R be an idempotent element such that A not equals to 0 and A not equals to 1. Right? But A is idempotent, so that means A square equals to A. So that means A times 1 minus A equals to 0. But A is non-zero and A is not equals to 1. So these two elements are non-zero and their product is 0. So this means A and 1 minus A are zero divisors in R. So they are zero divisors. That means they cannot be unique. But this implies A belongs to M. Both A and 1 minus A belongs to M. But we are in a local ring. So what are the other characterizations of local ring? So R comma M local, this implies 1 minus X is unit for all X belongs to the maximal ideal M. So this uh, so A belongs to M implies 1 minus A is unit and M is basically the set of all non-units. So that will imply 1 minus A does not belongs to M because M equals to the set of all non-units of R. But here we have got 1 minus A is also in M. So this is a contradiction. Which is a contradiction. So what went wrong? So we have assumed that A is non-zero and A is not equals to 1, but A is an idempotent. So that is the contradiction. So that means A equals to 0 or A equals to 1. So 0 and 1 are the only idempotent elements in a local ring. So this is one useful fact of local rings. Now let's see one more property of local ring. So that will be problem number 7. So again, let okay. So let R be a local ring. So we already know the definition of characteristic of a ring. So what can be the characteristic of a local ring? Then show that characteristic of R is 0. So that either characteristic of R equals to 0 or characteristic of R is a power of some prime number. So basically, characteristic of R equals to 0, or characteristic of R equals to p power n for some prime p and n natural number greater equals to 1. So that is what we have to prove. These are the only two choices for the characteristic of a local ring. So we already know, if we have an integral domain, then its characteristic is either 0 or a prime. But for a local ring, we are also in special cases. Okay, so let's prove this. So let R be a local ring whose characteristic is non-zero. So R be a local ring such that characteristic of R is non-zero. So then we have to prove that characteristic of R is a power of a prime. So we want to show characteristic of R equals to p power n for some prime number p and a natural number n greater equals to 1. So we will prove it by contradiction. So suppose, so not equals to 0 means it is a finite number, finite natural number. So to prove that it is a prime power, we need to prove that it has only one prime divisor. So for contradiction, suppose it has more than one prime divisor. Suppose characteristic of R equals to m and p comma q be two distinct prime divisors of m, right? So p and q are two distinct prime numbers. So then there exist uh, integers x and y such that px plus qy equals to 1. So because uh, p and q are distinct primes, so they are relatively prime, because pq are co-prime or relatively prime, right? Now m is the characteristic. Since characteristic of R equals to m, so that will imply m dot 1 equals to 0. But m we can write it as pq times d for some natural number d, because both p q divides m. So this imply pqd times 1 is 0. So this imply, okay, now let's this put equation as star. Okay, now px plus qy equals to 1. So that implies 1 minus px equals to qy. And let's put this equation as star. But from here, uh, so characteristic means m dot 1 equals to 0 and m is the smallest positive integer with this property. So this implies p dot 1 is a zero divisor of R because p dot 1 is non-zero and p times q times d is 0. And p dot 1 is non-zero because p is less equals to m and m is the characteristic. Strictly less than m and m is the characteristic. So that will imply p dot 1 is a non-unit. So p dot 1 must be in the maximal ideal. And here we have only one maximal ideal. This has to be the Jacobson radical of the ring R. So that will imply 1 minus px is a unit of R. But 1 minus px is equals to qy. This implies qy is a unit of R. But that will imply q is a unit of R. But from here, if we take this double star, but from double star, q we get as a similar reason, we get since p is a zero divisor, q is also a zero divisor. But here we are getting q is a unit. So this is a contradiction. So a zero divisor cannot be a unit. So that means characteristic of R cannot have two distinct prime divisors. Thus, characteristic of R must be equals to p power n for some p prime number and n greater equals to 1 a natural number. Okay, so this is about the characteristic of a local ring. So this is also not difficult to prove, but one has to be careful. Okay, now the other problems. Okay, this is so what are the remaining parts? So we have done Noetherian module, exact sequences, multiplicative set, localization, local rings. We have done Nakayama's lemma, and we have not done anything on prime spectrum. So let's do one or two problems on the spec of R, maybe some properties of spec of R. So this is problem number 8. So let R be a ring and let X be the prime spectrum of the ring R. Prime spectrum means the set of all prime ideals of R. And let's say A. Uh, so R equals to R1 cross R2, where R1, R2 are non-zero rings. And part B is R has uh, idempotent elements which are not equals to 0, not equals to 1. And part C is X is disconnected topological space. Then prove that A implies B implies C. So actually all these three statements are equivalent, but I will left one part as exercise for you. So A implies B. So what is A? So A is R is direct product of two non-zero rings. Then we need to show that it has uh, idempotent elements which are neither 0 nor 1. So since R equals to R1 cross R2, so 1 minus 0 and 0, sorry, 1 comma 0 and 0 comma 1 belongs to R. So these are idempotent elements. So these are idempotent elements which are not equals to 0 and not equals to 1. So here 1 is basically 1 comma 1, the tuple, and 0 is basically 0 comma 0 tuple. So A implies B is very easy. Now B implies C. So we need to prove that uh, this if R has idempotent elements which are non-zero, not equals to 1, neither 0 neither 1, then its prime spectrum has to be disconnected. So this is B implies C. So let E belongs to R be an idempotent element such that E is not equals to 0 and E not equals to 1. Now E times 1 minus E is basically E minus E square equals to 0, and 1 minus E is also an idempotent element. Okay, so we have got two idempotent elements. So now let I1 be the ideal generated by E and I2 be the ideal generated by 1 minus E. Then you can check that I1 intersection I2 is 0 and I1 plus I2 is basically the whole ring. So these are very trivial facts for you to check. Okay, now define phi from R to R mod I1 cross R mod I2 by phi of R goes to the tuple R plus I1 comma R plus I2. Then this is very well known map and its kernel is basically I1 intersection I2 which is 0. So then and you can use the Chinese remainder theorem to prove that it is an isomorphism. Phi is an isomorphism by the Chinese remainder theorem. So this is a well-defined map that is also routine check. Injectiveness will come from this intersection is 0 and surjectiveness will come from this coprimeness of I1 and I2. So R is isomorphic to R mod I1 cross R mod I2. So that will imply prime spectrum of R is basically, so there will be a bijective map from prime spectrum of R mod I1 cross R mod I2. This has a bijective map to prime spectrum of R mod I1 cross prime spectrum of R mod I2. And this is basically same as variety of I1. This is disjoint union variety of I2. This is disjoint. So prime spectrum of R is, so you can check these are non-empty proper closed subsets. So it is disjoint union of non-empty closed subsets. So this topological space has to be disconnected. So we have proved B implies C. So in fact, C implies A is also true. So this part is exercise. So these three are equivalent statements. So one thing, so if spectrum is disconnected, then the ring has a non-idempotent element which is non-zero and not equals to 1. And we have seen that in a local ring, only idempotents are 0 and 1. So if a space, if the spectrum is disconnected, then that ring cannot be local ring. So let me prove that as remark. So spec of R is disconnected, that will imply R is not a local ring. So there are other interesting property of this topological space, prime spectrum of the ring R. So one can check the exercises of the book Athia MacDonald. There is a big list of the properties as exercises. So one may try to solve them. But I think it's enough. So I think these exercises will also help you to solve the assignment problems. So just give it a try. So I think this is enough for this week 4. So I think we can stop here. Yes. Okay, so that's all. Let's stop here for today. So again, we will meet in the next week.